Rustam, can you start, please?
It's time already? All right. Wow, it's it's my pleasure to introduce my friend Manuel Mancini from University de Palermo from Italy. And this joint work is actually from our common friend as a collaborator, Xabier García Martínez. He's old supervisor, well, not that old, but team under Linden, and their joint student, PhD student, Corentin Vienne, and also we believe it's Jose Brox, right, from University
Yes,
de Valladolid. Yes,
yes.
so please, whenever you're ready.
Okay, good afternoon to everyone. Thank you, Rustam, for introducing me. And I want to thank all the organizers of the European Non-Associative Algebra Seminar to giving me the opportunity to talk here today and to present some of my results that I published in some papers. Also, you can find it in my PhD thesis that I defended the last year in Palermo. So we will talk about the representability of action, that is a categorical notion that you can find in semi-abelian category. And I will use this categorical notion to study action or split extension. We will see in this talk that they are essentially the same stuff in the context of non-associative algebras. So let's start with by recalling what is an actions or a split extension in the category of groups. So I think that you know that given two groups, an action of a group B on a group X is a map from Xi from B times X to X with denote the image of the pair Bx with the B dot X, and such that the first two equations tell us that this is an action of B on the set X. But then, since also X is a group, we know how to compute the action of B on a multiplication XX prime. So as the action of B on X times the action of B on X prime. Given an action, we can construct the semi-direct product with respect to this action, Xi, which is given by the Cartesian product of the set B and X with this multiplication that is defined in a unique way once we fix the action. Because inside this formula, you can find the product in B, the product in X, and the action of B on X. And then the unit of the semi-direct product will be the pair 1, 1, and we can compute also the inverse of a pair Bx. And we can associate with this action the canonical split extension given by the semi-direct product, which is, in this split extension, you can find the map I1 and I2 that are the canonical inclusion on the first and second component, and pi1 that is the canonical projection on the first component. So what we did is, we started with an action, and we defined the split extension. But we can also do the converse. So we can start with a split extension in the category of groups, and we can define an action from a split extension. Actually, the action is defined by conjugating element on X with element of B inside the group A. Indeed, we conjugate K of X with beta of B. And one can prove that the set of actions of B on X is in bijection with the set of isomorphism classes of split extension of B by X. So for this reason, in groups, action and split extension are essentially the same stuff. But moreover, we have another property in groups, in the category of groups, that actions are represented by automorphism, in the sense that if I take a split extension as above, I can define a group homomorphism from B to the group of automorphism of X, where the automorphism associated with the element B in B is given exactly by the action. So phi b of x is again the beta of b, k of x, beta of b inverse. So the conjugation between k of x and beta of b. But again, conversely, if I start now with a group homomorphism from B to out of X, I can define the semi-direct product associated with this group homomorphism, and thus I can define a split extension of B by X. So in group, we can talk about action, we can talk about split extensions, but we can describe both of them with homomorphism inside a group of automorphisms. So we want to generalize this study to other setting. And a good setting to study this notion, the notion of action and the notion of split extensions, is the setting of semi-abelian categories, which were introduced in order to provide a categorical setting which would capture algebraic properties of groups, rings, and algebras. You have to think that the main example of a semi-abelian category is the category of groups, as the main example of an abelian category is the category of abelian groups. I recall here, but I will not enter in the details in this talk, that a semi-abelian category is pointed, bar exact, Burr protomodular with finite coproducts. And in any semi-abelian category, we can introduce the notion of split extension. A split extension of B by X is a diagram of this kind in the category C, where the composition alpha beta is the identity of the object B, and the pair xk is a kernel of alpha. Now, what we can do is to fix the kernel of the split extension. In a split extension of B by X, X is the kernel of the split extension and B is the co-kernel of the split extension. So if I consider the split extension with fixed kernel X, I can define a contravariant functor from the category C to the category of sets. How this functor acts? So it takes an object B in C, and it associates with C the set of isomorphisms classes of split extension of B by X. And again, in any semi-abelian category, as it happens in the category of groups, actions on X and the split extensions with fixed kernel X are essentially the same stuff, in the sense that we have a natural isomorphism between the functor of split extension with fixed kernel X and the functor of an internal action on X. Here, actions means internal action. This is the categorical notion of actions. I will not talk here about the categorical notion of action because I will describe action and split extension in varieties of non-associative algebras. And in varieties, it is better to work with split extension. But you have to think that if I use this notion of internal action in well-known contexts like groups or rings or Lie algebra, for instance, I obtain the classical notion of actions in the category of the action in groups, action for Lie algebra, and action for rings. So let's start with some example of semi-abelian categories. I will talk about varieties of non-associative algebra that are examples of semi-abelian categories. So for me, a non-associative algebra is a non-necessarily associative algebra, in the sense that a non-associative algebra could be associative. And it is just a vector space over a field F. For me, the field will be a general field, but with characteristic different than 2. And this vector space is equipped with a bilinear operation, which is called the multiplication. I don't require anything on the multiplication, just the bilinearity. So in general, our algebras are not unitary. So we don't have a unit element. We denote by alg the category of non-associative algebras, where the morphisms are the linear maps which preserve the multiplication, so they are the algebra homomorphism. And I can define in what is an identity of an algebra A. Is a non-associative polynomial which vanished when I substitute to the variables elements of the algebra A. Now I take a set of identities and I can define the variety of non-associative algebras determined by this set of identities I, which is the class of all algebras which satisfy all the identities in I. And of course, what I can do is to see such a variety as a full subcategory of the category of non-associative algebras. This means that we have the category of associative algebra and we are adding equations. The equations are given by Bardet identities. And one can prove that any such variety is a semi-abelian category. So all the varieties of non-associative algebras are over a fixed field are semi-abelian categories. So let's see some examples of varieties of non-associative algebras. We had the first one that is the variety of abelian algebras, which is determined by the identity xy equal to 0. This is the only variety of non-associative algebra which is an abelian category. And this is because this variety as a category is isomorphic to the category of vector spaces over the field F. I will not put in our varieties the field F in the notation because the field is fixed. Then we have the variety of associative algebras, which is determined by associativity. Then we have commutative algebras and anti-commutative algebras. Then we can define the variety of commutative associative algebra by putting commutativity and associativity. Then the variety of Lie algebras, which is determined by the anti-commutativity, since I suppose that the field the characteristic of the field is not 2. Otherwise, I should have put x squared equal to 0. And then the Jacobi identity. Then we have the commutative counterpart of Lie algebras, which is the variety of Jacobi-Jordan algebras, which is determined by the Jacobi identity with the commutativity. And then we have a generalization of the notion of Lie algebra, which is given by Leibniz algebras. Here I will work with the right Leibniz algebras, which are determined by the right Leibniz identity. We can read this identity by observing the fact that the right multiplications are derivations. These Leibniz algebra were introduced by Lodin in 1992, but before they were considered by Bloch, who called them the algebra for the strict connect with the derivation. And we will see that the derivation in Leibniz algebra will be useful to describe actions, but they are not enough. And then we have a generalization of the notion of associative algebras, which are alternative algebras. And this variety is determined by these two equations. One can see a difference between these last two equations with the previous ones. All the equations that I put until Leibniz algebras are given by multilinear polynomials, while alternative algebra is not defined by multilinear identities. But since the characteristic of the field is supposed to be different than 2, we can use the multilinearization process to define alternative algebras with the multilinear identity. And this is something that we will do in this talk, at the end of this talk. So what I will study in varieties of an associative algebra, I will study the notion of representability of actions. This is a categorical notion. A semi-abelian category is said to be action representable if for every object x in C, the functor of split extension by x or internal actions on x is representable. This means that for every x, we have an object which is called the actor of x, such that we can represent action by with the morphism with the codomain this actor bracket x. This means that we have a natural isomorphism between the functor of split extension with fixed kernel x and the morphism in C with the fixed codomain the actor of x. And the prototype examples of action representable categories are the category of groups and the category of Lie algebras over a field F and any abelian category. In groups, we see in the first two slides that actions are represented by automorphism. This means that the category of groups is action representable and the actor is given by the group of automorphism of X. In Lie algebra, we can use the same argument to prove that actions are represented by derivations. In any abelian category, actions are trivial, and it is possible to prove that the actor of X is the zero object, that is the initial and terminal object in the category. But if I apply this notion to varieties of non-associative algebras, it is possible to prove that this notion is quite restrictive. Indeed, it was proven that over an infinite field with the characteristic different from 2, the only action representable varieties of non-associative algebras are the variety of abelian algebras and the variety of Lie algebras. If I consider also the case characteristic equal to 2, we have to add one variety, that is the variety of quasi-Lie algebras. But in characteristic different from 2, quasi-Lie algebra is equivalent, are equivalent to Lie algebras. So we don't see the third variety for this reason. So this notion is quite restrictive. And 3 years ago, Janelidze introduced a new notion, which is the notion of weakly action representable category, which includes a wider class of semi-abelian categories. We have essentially the same notion of before, but now we don't have a natural isomorphism, but just a monomorphism from the functor of split extension with fixed kernel X and the functor of morphism in the category C with fixed codomain T. T is again an object which depends on X, so I should have written T of X. And this T is called weak actor of X. The pair T tau is called a weak representation of the functor of split extension with kernel X, and a morphism from B to the weak actor T, which belongs to the image of a component tau B. This means that a morphism which comes from a split extensions is called an active morphism because it is representing an action. I want to observe that this weak actor is not unique. If I consider a weak actor and I find a monomorphism in the category C from T to T prime, then the codomain T prime is another weak actor. So the weak actor is not unique. And this is the difference with the notion of action representability, where the actor is unique. The first trivial example of action representable of weakly action representable category is any action representable category, because the actor is a weak actor. But we can find 2 non-trivial examples. The first one is given by Janelidze in his paper. He proved that the category of associative algebras is weakly action representable. And a weak actor of an associative algebra X is the associative algebra of bimultipliers of X. What is a bimultiplier? It is a pair of 2 linear endomorphisms of the algebra X, such that the first one is a multiplier. Multiplier means that this endomorphism is X linear on the left. The same for the second one, that is called anti-multiplier, which is X linear on the right, and together they are compatible. Compatibility is expressed by this third identity, and if I write the 2 linear maps in this way, like left and right multiplications, you can see that the compatibility can be expressed like an associativity, but an associativity between 2 elements of X and 1 element that is a function, it is a linear map. In one of my papers with Alan Cigoli from University of Turin and Beppe Meter from University of Milan, we proved that the category of Leibniz algebra is weakly action representable. As I mentioned before, derivations are useful to represent action, but they are not enough. To represent action, in Leibniz algebra, we have to use the so-called biderivation. This is a notion which were introduced also by Lodé in the same paper where he introduced Leibniz algebras. What is a biderivation? It is again a pair of 2 linear endomorphisms of X. The first one is a derivation. The second one, capital D, is an anti-derivation. And you have to think that right multiplications are derivation, and left multiplication in right Leibniz algebra are antiderivations. And again, we have a compatibility, which is expressed by this third equation. But at this point, one can ask, is any variety of non-associative algebra weakly action representable? The answer is no, because a counterexample is given by Jordan algebras. I recall that a Jordan algebra is a commutative algebra which satisfies the Jordan identity. And how we can prove that this variety is not weakly action representable? By recalling that any weakly action representable category is action accessible. This is another tool that we have to study actions. This is a weaker notion. In a paper by Cigoli and Mantovani of 2012, they proved that the category of Jordan algebra is not action accessible, and so we can put everything together to conclude that this variety is not weakly action representable. And it is possible to do this with every variety of non-associative algebra which is not action accessible, of course. So now we want to study action in a general variety of non-associative algebras. So we fix a field with a characteristic different from 2. We take a variety of non-associative algebras over the field F. And we have to do some restriction. We have to put some restriction in our variety. So we will suppose that our variety is operatic. Operatic means that all the identities of the varieties are multilinear, so they are expressed by multilinear polynomials. But this is not too restrictive because, for instance, in characteristic 0, every variety is operatic. Again, this is due to the multilinearization process. Moreover, we have to suppose that the variety is action accessible, because otherwise it is not weakly action representable. But action accessibility is a categorical notion. We want to find the algebraic counterpart of action accessibility for varieties of non-associative algebras. This equivalent in varieties of non-associative algebras, action accessibility is equivalent to the fact that the category is an Orszag category of interest. This means that it is a category of group with operation with some axioms, but we don't care about this in this talk. In this talk, we will use this characterization of action accessible varieties of non-associative algebras. This is equivalent to saying that the lambda mean rules holds in the variety. What this means that we can find 16 constant in the field F such that we can express both x times yz and yz times x as a linear combination of multiplication between x, y, and z in such a way in the second component x is never isolated. If you look at the second component, x is every time inside a bracket. So action accessibility in varieties of algebras means that we have at least 2 identities of degree 3 in the varieties, 2 special identities of this kind. The fact is that this choice of the parameters lambda 1, lambda 8, mi1, mi8 is not unique. We can find different lambda mean rules. So in our talk, we have to fix a choice of the lambda mean rules. For instance, in associative algebras, we can easily find the lambda mean rules because we can take lambda 1 equal to 1, mi8 equal to 1, and all the other coefficients equal to 0, and so we have associativity. Let's investigate the commutative case, because in the commutative case, the lambda mean rules reduce to just one equation to 2 coefficients alpha and beta. So we can observe, it is really easy to prove that from this equation we can conclude that the variety is associative or satisfies the Jacobi identity. So any action-accessible variety of commutative algebra is a subvariety of the variety of associative algebra or a subvariety of the variety of Jacobi-Jordan algebras. If, moreover, we suppose that the characteristic is not 3 and V is quadratic, quadratic means that all the identities of V are of degree 2 or 3. 2, in this case, is given by the commutativity, and 3 is given by the lambda mean rules. So we don't have other identities. Then we have just three varieties with this property: the variety of commutative associative algebra, the variety of Jacobi-Jordan algebras, and the variety of two-step nilpotent commutative algebras. The representability of action in commutative associative algebras was studied by Borso, Janelidze, and Kelly. They proved that split extension or action of commutative associative algebras can be represented by with morphism with codomain an associative algebra that is called the algebra of multipliers of X. This is the commutative version of bimultipliers. So when an associative algebra is commutative, it is better to consider multiplier instead of bimultipliers. So we have just one, in this case, one linear map, which is linear on the left or on the right, X linear on the left or on the right. So we can take out X or Y. The fact is that we have something that is very close to action representability because we have a natural isomorphism between a split extension and morphism inside an object. So this is something that is very close to be the actor. But the fact is that this home functor lives in the category of associative algebra. It does not live in the category of commutative associative algebras because this algebra is not commutative. Here, the operation inside M of X is given by the composition of function. So one can prove that M of X is a commutative algebra if and only if the functor is representable. It is easy to find some examples where this algebra of multiplier is commutative. For instance, if the annihilator of the algebra X is trivial or X is a perfect algebra means that X squared is equal to X, then M of X is commutative. But at the same time, if one take the abelian two-dimensional algebras, then M of X is not commutative. And since we found an example of a commutative associative algebra such that M of X is not commutative, one can conclude that this variety is not action representable. Now, we can study the action in the variety of Jacobi-Jordan algebras, which were the second example of action accessible quadratic commutative varieties of algebras. So we take a Jacobi-Jordan algebra, so a commutative algebra with the Jacobi identity. Since they are the commutative counterpart of Lie algebras, we can expect that we will use something that is very close to derivation to study actions. And here we use the notion of antiderivation. One can examples of antiderivation. An example of antiderivation is given by the so-called inner antiderivation that are the left multiplications. So how to study action? So we will study action by studying split extensions, because if I take a split extension of Jacobi-Jordan algebras, then, as it is possible to do in every varieties of algebra, I can represent A up to an isomorphism of split extensions as a semi-direct product, as the semi-direct product between B and X, which is the algebra defined on B plus X, the direct sum of vector spaces, with this multiplication. This multiplication is defined uniquely defined once I fix the multiplication in B, the multiplication in X, and this operation, this star operation, which is given by a bilinear map. The bilinear map is defined with the map that we used in the split extension, the map beta and k. So it is like we are multiplying, we are doing the multiplication between B and X inside A, something that was very similar in the category of groups. Now we can do another, we can see another thing. So now let's do the converse. Now let's start with B and X to Jacobi-Jordan algebras, and we define this multiplication in B plus X. And we ask when this multiplication define a Jacobi-Jordan algebra structure. one can prove that b plus x with this multiplication is a Jacobi-Jordan algebra, if and only if two equations holds. The first one tells us that the algebra B acts on the algebra X via antiderivation. Moreover, the action of BB prime, of a multiplication BB prime, is given by the so-called anti-commutator between the action of B and the action of B prime. So one can define a split extension as a linear map from the B to the space of antiderivation of X, such that this equation solves. So we can multiply actions using the anti-commutators. And the anti-commutator is defined as the commutator in Lie algebra, but we have a second minus here. So the situation is very similar to what we have in Lie algebras, but there is a difference, because in Lie algebras, derivation with the commutator form a Lie algebras. Here it is not true. So in general, the anti-commutator between two antiderivation is not an antiderivation. So in general, the space of antiderivation with the anti-commutator is not an algebra. Or it can be an algebra, but it could not be a Jacobi-Jordan algebra. For instance, for the abelian one-dimensional algebra, the space of antiderivation does not satisfy the Jacobi identity. So again, the object that allows us to describe actions is not an object of the category. In this case, because the multiplication that we require is not an internal operation. So what we can do is to restrict ourselves to consider the antiderivation such that if I apply the anticommutator, I obtain again an antiderivation. So we are restricting the domain of our bilinear multiplication. And so we are using the notion of partial algebra. A partial algebra is a vector space with a bilinear partial operation. So an operation which is defined in a subspace of x times x. An homomorphism of partial algebra is a linear map which preserves all the multiplications that are well defined. So this equation solved every time both xy and f of x times f of y are defined. We can define the category of partial algebra in the obvious way, and this allows us to describe actions in the category of Jacobi-Jordan algebras, because we can prove that actions are the same of morphism with domain a Jacobi-Jordan algebra, but with codomain the space of antiderivation with the anticommutator, which is a partial algebras. But we can use here, we can fix the situation by using the forgetful functor, because any Jacobi-Jordan algebra is of course a special partial algebra, so it is what we call the total algebra. In the special case, the space of antiderivation with the anticommutator is a Jacobi-Jordan algebra, then this home functor becomes the home functor in the variety of Jacobi-Jordan algebra, and then we obtain action representability. Now, let's go to the third and final example in the commutative case, that is the variety of two-step nilpotent commutative algebras. In this case, the situation is easier because we prove that the variety is weakly action representable, and a weak actor is given by an abelian algebra. So in this case, we have an object of the category because we have an abelian algebra. Abelian algebra, recall, this means that the multiplication here is the trivial one, f dot g equal to 0. We characterize the morphism which comes from an action, so the active morphism. So a morphism is an active morphism if and only if it satisfies this equation. And again, this equation is related to the equation which describes the variety. The variety is the variety of two-step nilpotent commutative algebras. So we have the equation xyz equal to 0. So it is like that equation. So the product of three elements is 0, but this multiplication is done with one element in X and two elements in B. So one could start to understand that the characterization of active morphism and also the study of the representability of action is strictly connected with the set of identities which define the variety. I will not describe in details the anti-commutative case because it's very similar to the commutative case. Also in that case, we obtain 3 examples, but I will go directly to the non-commutative case, so to the general case. So I fix an operatic and action-accessible variety of non-associative algebras. Operatic means that all the identities are multilinear. I am fixing a choice of the lambda mean rules. So the choice of 16 constant with 2 identities of degree 3. And in general, I will have a set of multilinear identities which determine the variety. So I will denote the identity by phi of ki, where k is the degree of the identity. So what we want to do is to generalize the construction of bimultipliers for associative algebras and biderivation for Leibniz algebra to a general variety of non-associative algebras. So we want to construct a subspace of the space of copies, 2 copies of linear endomorphism of X, together with the partial operation, because we will see that in general we don't obtain a internal operation, which allow us to describe action or split extensions. So again, we fix a split extension in the variety V, and again, it is convenient to describe the split extension as a semi-direct product. And again, in the semi-direct product, we will find 2 operations, and these operations are done again with 1 element in B, in the algebra B, and 1 element in the algebra X. How to define this B star X prime and X star B prime? Again, with some bilinear maps. Here we will have 2 bilinear maps. In the commutative case, the bilinear map was just 1, because commutativity implies that L is equal to R. In the anti-commutative case, R is equal to the opposite of L. Here we have 2 distinguished bilinear maps, but both of them are uniquely defined once I fix the split extension, because we define them using the maps beta and k of the split extension. Again, we do the same of what we saw in Jacobi-Jordan algebras. So we start with 2 algebras in the variety, B and X. We construct this semi-direct product, and we ask which are the conditions such that the semi-direct product is in the variety. So define an algebra in the variety. And again, the situation is strictly connected with the identities satisfied by the variety V, because the semi-direct product is an object of V if and only if all the identities of the varieties are satisfied by the elements of the semi-direct product. But it is sufficient to verify these identities when we substitute to the variables alpha 1, alpha k, either element of the form 0x, so element which comes from the kernel of the split extension from X, or element of the form which comes from B, so of the form B0. So it is like we multiply element in B with element of X, but this multiplication is done inside the semi-direct product. So we will use the following notation. A multiplication between B0 and 0x will be denoted by B star x. And a multiplication between 0x times B0 will be denoted by X star B. So we are ready to define the partial algebra E of X. Now you will understand why there is this E in the notation. So how to define E of X? We have to use the identities of the variety. So we take a subspace of nx squared. So our objects will be pairs of linear endomorphism of X. And it is useful to use this notation as left and right multiplication, because then it is easy to compute this calculation to understand which are the elements of V of X, because we will use the identities of the variety. So, and such that, so this pair satisfy all the identities of V when we substitute to alpha 1, alpha k, in exactly one spot, alpha j, I will put f. In all the other spots, so in all the other entries, alpha t with t different than j, I put element of x. And I will do this for every j from 1 to k. So I have the first time I have to put f in the first component, then in the second component, until I arrive at the place alpha k. Then I have to do computation. And inside these identities, at some point, I will multiply f with an element of x. So we will find an expression of the form fx or an expression of the form xf. If I have to compute fx, this means the first component of f, so f star x. F star x means the linear map f star applied to the element x. In the same way, xf means the second component applied to the element x. So I obtain a vector space. Then I have to define a bilinear map. I have to define a bilinear partial operation. At first, I defined a bilinear map which is not an internal operation. And to define this bilinear map, I use the lambda mu rules that I fixed before. So I recall to you that I fixed the coefficient lambda 1, lambda 8, mi1, mi8. So in this way, we understand that the construction of the vector space is the same, also if we change the choice of the lambda mu rules. But if I change the lambda mu rules, then I obtain different bilinear maps, different operations in E of X. So it is important to fix the lambda mu rules. If I do this construction in the associative algebras with the obvious choice of the lambda mu rules, then I obtain that E of X is isomorphic to the associative algebra by multipliers of X. So I obtain in this case that the operation is well defined. Again, in Leibniz algebras, I obtain something that is isomorphic to the Leibniz algebra of biderivations. So this makes clear that we are very close to an object, E of X, that allow us to represent actions. But now we have to go in the general setting. So we have to go to the case that this bilinear map is not an internal operation. So if it is not an internal operation, then what we do is to restrict the domain of this bilinear map to the pre-image of the inclusion of E of X inside and X squared. In this way, we obtain a bilinear partial operation, and so we obtain a partial algebra. This partial algebra, we can see the construction of this partial algebra in the case of alternative algebras, because in alternative algebras, we obtain a partial algebra which is not a total algebra. So we consider the variety of alternative algebras. If we apply the multilinearization process, we obtain a way to describe alternative algebras with the multilinear identities that are complicated. Maybe it is better to describe it in general with the non-multilinear identities, but if we want to construct this object E of X, we are forced to go to multilinear identities. So we construct E of X. So we have to take a pair of linear endomorphisms of X satisfying these four equations for every x, y in X. And then we have to define the bilinear map. that is given by these two equations. The first equation is for the first component, and the second equation is for the second component. I think by taking the abelian two-dimensional algebra, one can check that this operation is not internal, is not well defined. So this means that if I take two elements inside E of x and I apply this operation, then the result is outside E of x. So I obtain a partial algebra which is not a total algebra. But if I restrict myself to unitary alternative algebra, so if I consider alternative algebras which has a unit, then I can use the unit to reduce my equations, and in this case, E of x is very simple to describe because one can prove that E of x is just isomorphic to x. So in this case, we will see that this means that the actions on a unitary alternative algebras are representable. So let's conclude with our main theorem. So for a general variety of non-associative algebra that is, of course, operatic, so with multilinear identities and action accessible, we found a way to describe action. But we describe actions in a way that is very similar to weak action representability of Janelidze. So we have a natural monomorphism from split extension to an home functor. But this home functor lives outside the variety because the codomain of this morphism is given by a partial algebra, which in general is not a total algebra. But the interesting fact is that if I consider an active morphism, so a morphism of this kind, a morphism which comes from an action, the image of this morphism, which is a subspace of E of x, is an algebra of the variety. And this is okay for us because if we want to work with action, we don't consider all the codomain, but just the image of the active morphism. Then again, we obtain also in this general case a characterization of the active morphism, a characterization which is given in terms of identities satisfied by the variety V. And in the special case, E of x is an object of the variety, then we obtain the notion of weak action representability of Janelidze, because then in that case, the home functor becomes the home functor in the variety V. So since this is very similar to weak action representability, the only difference is that this E of x lives outside the variety, we called E of x the external weak actor of x. So this is the reason why there is this E in the name. If tau is a natural isomorphism, then E of x becomes something that is very similar to an actor. But again, it is external, so we called it external actor. So one can check that in abelian algebra, the construction gives the zero algebra, which is the actor of x. In Lie algebra, E of x is the Lie algebra of derivation, so it is the actor. In commutative associative algebra, we obtain the associative algebra of multipliers of x, which is an external actor. In Jacobi-Jordan algebra, we obtain antiderivation and again an external actor. In two-step nilpotent commutative algebras, we obtain a weak actor. And in alternative algebras, in the case that the alternative algebra is unitary, as we proved before, we obtain in this case, that actions of unitary alternative algebras are representable. So, in this way, one can see that, for instance, actions on octonions algebras, which is a unitary alternative algebras, are representable. Now, I want to reflect on this question. What happens if the object E of x is not an object of the variety? Because if it is an object of the variety, for every x, then the variety is weak action representable. But is the converse true? So if it is not in the variety, then the variety is not weak action representable. Let's start with the example of Leibniz algebras. In Leibniz algebras, we obtain, as I said before, the Leibniz algebra by derivation of x. This was not 100% true, because this is true if I choose the lambda mean rules in this way. This is the standard way to present Leibniz algebras. So with the right Leibniz identity written in the way we need for the lambda mean rules. So in this way, I define the multiplication in E of x. So in the vector space of by derivation, I define a multiplication. And in this case, this multiplication defines a Leibniz algebra structure. And so we have a weak actor. But if I change the lambda mean rules, I can present the same variety in a different way. For instance, here I'm changing just one monomials. This one, the last one, minus yxz can become plus yzx. These two pair of identities define the same varieties, which is the variety of Leibniz algebras. But if I do the construction in this way, then I obtain a multiplication which does not define a Leibniz algebra. So, in this case, with this choice of the lambda mean rules, E of x is not an object of the variety, but the variety is weakly action representable. But one can say, okay, but this is because you have another choice of the lambda mean rules which allow you to have an object in the variety. So let's do another examples. Commutative associative algebras. In commutative associative algebra, we had multipliers. Multipliers is an associative algebras which is not commutative. So in this case, E of x does not live inside the variety. And if I change the lambda mean rules, I never obtain an object of the variety. So for every choice of the lambda mean rules, the object E of x, the external weak actor, does not belong to the variety of commutative associative algebras. But we prove that this variety is weakly action representable. So if one consider the external weak actor and the external weak actor is not in the variety, one cannot conclude that the variety is not weakly action representable. The fact is that we didn't conclude this statement using the external weak actor. We start with the external weak actor, but then we use the so-called amalgamation property. So we construct the external weak actor as a colimit. So the construction is complicated. So for me, it is better to describe action by using the object E of x, because you have linear maps which can be described by matrices, for instance. So let me conclude with some open problem and future directions. So we have an open problem. We know that every weakly action representable category is action accessible. And we have a counterexample that shows that the converse implication does not hold. It is the example of n solvable groups, which was given by James Gray. But at the moment, we don't have an example of a varieties of algebras which is action accessible but not weakly action representable. And so this is one of our open problem. Then we would like to generalize the construction of this external weak actor to algebras with more than one operation, for instance, two operations. And the moment with Alan Cigoli and Beppe Metere, we did this construction for Poisson algebra and commutative Poisson algebras, but we think that it's easy to generalize this to other varieties. And then I am moving to study actions to a more general context, that is the context of ideally exact categories, which generalize the notion of semi-abelian categories and allow us to include in this setting also non-pointed category. For non-pointed, I mean categories with more than one constant. For instance, unitary rings. Unitary rings are not semi-abelian because we have 0 and 1. Then we can find inside this context some categories which you find when you study multi-valued logic, for instance, MV algebras that are connected with the Lukasiewicz fuzzy logic. And then inside this setting, we find categories of algebras with unit. And I proved already that in this context, you have more than one example of category of unitary algebra, which is action representable. So it seems that if you add unit, the notion of action representability is not too restrictive. So this is everything. I leave here some references, and I want to thank you for your attention.
Thank you very much for interesting talk.
Thank you.
Are there any questions? I have a small question. So at the end, you said about generalization. Does it make sense to consider this question for n-ary algebras, where the bracket is not binary but ternary, etc., like n-Lie algebra or Leibniz n algebras?
Yes, I think that you should put some hypotheses. Maybe consider that they are an Orszag category of interest, because to have this construction, you have to you need some hypothesis in the identities that they satisfy. But I think that it's possible. Maybe at this point you will find not a pair of linear maps, but
Yes, several could be several, right?
yes, maybe it can be difficult to compute then E of X, the object by ends, but maybe with some computer program you can do it, because in the end it's just linear algebra stuff.
I see. How about symmetric Leibniz algebras? Because then you have two identities, right? The left one and right one. Does it help somehow to reduce the problem instead of just Leibniz algebras?
And it does not reduce the problem, because then you should describe split extension of symmetric Leibniz algebras. So you have that the kernel is symmetric, the cokernel is symmetric, and you want also that the middle term is the semi-direct product is symmetric. And I recall that with Xabi we did some computations, but what we obtain is something very wild, because you have something that is the intersection of B derivation defined for left Leibniz algebras by derivation defined for right Leibniz algebra. The definition is similar but different, and then you have compatibility. But if I don't make a mistake, in the end, this is not a symmetric Leibniz algebras.
I see.
And so
By
again,
the way,
sì,
what do you
sorry.
use for computations? What kind of software do you use?
Mathematica.
Okay,
Yes.
great.
We did also create a program that allows you to find all the possibility for the lambda mu rules, and this program can construct to you this E of X, because in low dimension you can construct it by ends, but then it becomes hard computations. But with this program tells you if the multiplication is well defined, and if this object satisfy the identities of the varieties. So it's very useful. You put inside the identities, and then you have everything. So you have to put the identities, a basis for your algebra, and the brackets. So the multiplication between the elements of the basis.
Are there any questions again? If not, then let's thank the speaker, and well,
Thank
it
you.
was a great talk, so great to see you again.
Thank you, Rustam. So I stopped sharing. Okay.